Good morning, champs. In the previous video, we built the mathematical toolkit of fluid mechanics: gradient, divergence, curl, and the Laplacian. Today, we use those tools to understand the governing equations of fluid dynamics. The goal is not to solve complex flows yet. The goal is to understand what these equations mean physically and why they sometimes appear in different forms in the literature. Every advanced topic we will study later, such as creeping flow, vortex flow, and potential flow, is simply a special case of the equations we introduce today. We begin with conservation of mass. Mass cannot be created or destroyed. When we apply this principle to a small differential fluid element, we obtain the continuity equation. In differential form, it is written as partial rho over partial t plus divergence of rho times u equals 0. The first term represents the local time rate of change of density. The second term represents the net mass flux leaving a small control volume. If more mass leaves than enters, density decreases. If more mass enters than leaves, density increases. That is all this equation says. For incompressible flow, density is constant. In that case, the equation simplifies to divergence of u equals 0. This does not mean velocity is 0. It means the flow does not locally expand or compress. What flows in must flow out. You may also see the continuity equation written using the material derivative as d rho over dt plus rho times divergence of u equals 0. This form is mathematically equivalent. There is only one mass conservation law, written in different but equivalent forms. Now we move to conservation of momentum. This is simply Newton's second law applied to a fluid particle. Force equals mass times acceleration. In differential form, the general momentum equation can be written as rho times du over dt equals divergence of sigma plus rho f. The left side represents inertia. Rho is mass per volume. Du over dt is the material acceleration, which includes both local time change and convective change due to motion through a velocity field. The stress tensor sigma can be decomposed into minus p times the identity tensor plus tau, where p is pressure and tau represents viscous shear stresses. Substituting this decomposition gives rho du over dt equals minus gradient p plus divergence of tau plus rho f. This form clearly shows pressure forces, viscous forces, and body forces. If the fluid is Newtonian, incompressible, and has constant viscosity, the divergence of tau simplifies to mu times the Laplacian of u. Under those assumptions, the equation becomes rho times partial u over partial t plus rho times u dot gradient u equals minus gradient p plus mu Laplacian u plus rho f. This is the Navier-Stokes equation. It is the central equation of fluid mechanics. Every flow model we study later is obtained by simplifying this equation under specific assumptions. On the left side, we have inertia, local acceleration, and convective acceleration. On the right side, we have pressure forces, viscous diffusion of momentum, and body forces such as gravity. In the literature, you may see different forms of the Navier-Stokes equation. For example, in conservative form, it may be written as partial of rho u with respect to time plus divergence of rho u equals minus gradient p plus divergence of tau plus rho f. This form is common in computational fluid dynamics. You may also see the equation divided by density, introducing the kinematic viscosity nu equals mu over rho, giving these forms are mathematically equivalent when continuity is satisfied. The differences arise from rearranging terms, dividing by density, or choosing conservative versus non-conservative form. Finally, consider one important limit. When the Reynolds number is very small, inertia becomes negligible compared to viscosity. In that case, the momentum equation reduces to minus gradient p plus mu Laplacian u equals 0. This is the governing equation for creeping, or Stokes flow. The governing equations of fluid dynamics are simply statements of conservation of mass and conservation of momentum. If you understand the physical meaning of each term, the equations stop being intimidating. In the next video, we will begin applying these equations to specific flow regimes and see how systematic assumptions simplify them into powerful models.